All right, good morning, everyone. Really want to thank you all for the time that you've taken to jump on the call this morning here. Turnout for this is excellent, far and away the highest numbers that we've had on any of our previous webinars. So really appreciate all of you guys jumping on the call here today. For those of you not familiar with Fox Valley Metrology, we are a calibration, repair, and equipment sales lab headquartered in Oshkosh, Wisconsin. In addition to that, we've actually got 5 total locations throughout the U.S. We've been in business for about 25 years, primarily selling calibration, repair services, as well as equipment sales of any precision measurement instruments that you guys may have. Those of you not familiar with me, my name is Steve Toll. I'm the Vice President of Sales here at Fox Valley Metrology. And I welcome you all to join in the Thread Inspection Fundamentals webinar, which is the next in our series of monthly webinars that we've been doing, which are all a deep dive into industry topics about the science of measurement, auditing and accreditation best practices, quality management tips and tricks, industry technologies and trends, and so much more. Make sure you guys stay tuned for next month's webinar, which is going to be titled SBC in 3 Steps, Learning Statistical Process Control. That's going to be on September 29th at 10 a.m. and it's going to be hosted by Midatoyo. As for our agenda today, it's going to be presented by myself, and we're going to be doing a deep dive into the thread inspection world. You're definitely going to be finding some value out of this, whether you're new to the world or an entirely grizzled veteran. So today we're going to be diving into some thread form topics, discussing the designation nomenclature that are assigned to specify the thread form. We're going to go into the theory of thread inspection. We're then going to talk quite a lot about thread plugs, how they're designed and how they're used. And then, of course, talking quite a lot about their counterparts, thread rings, and how those are designed and used. Just some general housekeeping notes. All of you guys are muted right now, just out of respect for everyone on the call. As I already mentioned prior to this meeting starting, there is a Q&A available on the left-hand side of your screen. If you want to go ahead and use that at any point throughout the conversation to ask any questions, make any comments, bring up any topics that you'd like to discuss further, please feel free to do that. I've got a team of people that are there monitoring those. And then during breaks in the presentation, we'll also be picking a handful of those to address over the actual presentation here. So to go ahead and get yourself familiar with that, why don't you guys go over there and comment if you got any great Labor Day plans coming up for the upcoming weekend here. Also, this webinar is being recorded for future reference, so you're going to be able to go ahead and come back to this at a later date if you want to go through anything. Also, you're going to be able to share it with colleagues that may not have been able to get on the call or anything like that. Additionally, there's going to be an email that goes out after the webinar is complete. That's going to contain a link to download that recording, as well as a link to our special offer. So as I mentioned there is a special offer at the end of the call, so please make sure you stay tuned for that. Once the webinar is ended, it's going to redirect you to that page where you're going to be able to go ahead and redeem that offer. Also, that email I mentioned earlier is going to have a link directly to it. But of course, you can always contact myself, your local sales rep, or really anyone at Fox Valley Metrology to go ahead and take part in that offer as well. All right, so diving right into the content here, let's just go ahead and take a moment to be honest with ourselves. How many of you assumed, just like myself, that a bolt is really just a bolt, or a nut is really just a nut? I mean, it's pretty easy stuff, right? Well, after all, you can buy a 10-pack of those things for like $1 down at the hardware store. However, when you really start to drill down into it, you'll find that thread measurement is actually a highly complex and fascinating world. Threading is, excuse my pun here, quite literally what holds the entire industry together. As such, it goes without stating the importance of having accurately produced threads is incredibly high. So why don't we dive right into what the basics of a thread even is and look at the thread form. So right here, you've got the profile of a very basic thread. The first attribute that we'll look at here is the crest. So this is the height of which an external thread is raised, or the depth at which an internal thread is indented. The root is the deepest part of the thread groove. The flanks are the sides of the thread form connecting the crest to the root. The flank angle is, of course, then the angle at which the flank, or the angle between the flank and a line perpendicular to the axis of the thread. And then next up, we've got the pitch. So the pitch is the distance between corresponding points of adjacent threads. So it's important to note that rarely are all of these specifications being called out in a specification. That would obviously just take up a ton of room anywhere you're trying to do that and create a lot of additional work. So the good news is there's actually nomenclature systems out there available which address each one of these things within the nomenclature itself, which makes it very easy and very quick to specify things about a thread. So when we're looking at an external thread, there are a couple main key components with the external thread. First and foremost is the major diameter. So what this is the distance between a line that touches the crest on either side of the thread form. This is the largest diameter of the thread. The major diameter dictates all other dimensions, both internal and external, of a thread design. The minor diameter, on the other hand, is the distance between a line that touches the roots on either side of the thread form. This is the smallest diameter of the thread. The minor diameter of an external thread must clear the mating component's internal thread minor diameter in order for the two components to mate together. And then finally, we've got the pitch diameter. So this is the distance between a line that splits the crest and the root on either side of the thread form. The pitch diameter controls how tight of a fit there is between the two mating components. So an internal thread is very similar, just with some key differences here, is that the major diameter is actually the distance between a line that touches the roots on either side of the thread form. And this is the largest diameter of the thread here. The major diameter must clear the major diameter of the mating component's external thread. The minor diameter, in contrast, is the distance between a line that touches the crests on either side of the thread form. This is the smallest diameter of the thread. The minor diameter controls the strength or the shear of the design. And finally is the pitch diameter. This is the distance between a line that splits the crest and the root on either side of the thread form. The pitch diameter controls the tightness of fit on the mating components. So the last specification that has yet to been addressed is the quantity of threads that are in a given distance within the thread design. So in the imperial system, we use threads per inch, which is just simply that it counts how many threads exist within an inch on the given thread design. And then there's also the pitch, which, as described earlier, that's a distance between corresponding points on any adjacent threads. This is what the metric system uses. So as I mentioned earlier, rather than going through and specifying each one of those individual components on every single thing that an engineer is coming up with, or that you in the quality world have to inspect, luckily they've come up with different nomenclature systems out there that are going to allow us to actually specify all these things very quickly. So there are two primary nomenclature systems in existence. There's imperial and metric. Now, of course, in the US, we got to make things difficult, and that's why we came up with the imperial system. However, pretty much the entire rest of the world utilizes the metric system, with some exceptions mixed in there. So let's go ahead and break down the imperial designation nomenclature system. You can see here a very common call out of what an imperial thread would look like, 1/4-20 UNC-2B. So let's break down each one of those things individually. So the first listing is the nominal diameter. So this is basically the theoretical diameter from which the design size limits are derived and the application of tolerances and allowances are given. This number is really just the nominal size of the major diameter of the thread. So the next thing listed then is the threads per inch. Again, we already discussed this. This is just simply the threads that exist within an inch of the thread design. However, the next one gets a little bit more involved. So this is our thread series. So basically, there are numerous different types of thread series in existence. They're going to go more or less tweak the exact manufacturer of the thread design that we're discussing here. So some of the common ones are going to be listed here on this page. So we've got UN, which is the constant pitch series, UNC, which is the coarse pitch series, UNF, which is the fine pitch series, UNEF, which is the extra fine pitch series, UNJ, which is the constant pitch series with a rounded root and external threads on external threads and thread ring gauges. The UNJC is the coarse pitch series with a rounded root on external threads and thread ring gauges. UNS is a special diameter, pitch or length of engagement. UNJF is the fine pitch series with a rounded root on external threads and thread ring gauges. And UNJEF is an extra fine pitch series with a rounded root on external threads and thread ring gauges. So as you can see, each one of these calls out something a little bit differently, generally speaking, with how the pitch is done, as well as the roots and et cetera, et cetera. So not that you guys need to learn and know what every single one of these designations are. Most of them are going to fit within the first couple of listings that you see on this page. The next designation is for the class of fit. So basically what the class of fit is defining is how loose or how tight should the two mated components fit together. And these kind of exist on a range here, anywhere from very loose to very tight. So there are three primary designations that are used to call this out. The first one is just the number 1. So this is used where the applications where a liberal tolerance is required to permit easy assembly, even if the threads are slightly marred. So basically, this is somewhere where you don't really need to be super precise and you don't need to be really super accurate, because the actual fit of the two mated components, simply put, just aren't going to make that much of a difference on the outcome of the product. Also, there's an additional allowance added into this for fit on externally threaded components. The next one is the number 2. So most commonly, this is the class that is used for general applications. And the same as class 1, there's an additional allowance given for external thread components. And this is really most commonly referred to as the nuts and bolts fits, the nuts and bolt fit. This is because the guaranteed gap between the mating components where the tightness is accomplished is by contact against a face. So, throughout the manufacturing industry, this is going to certainly be the most common class of fit that you see designated. And finally, we've got class 3. So this is for highly precise applications where the accuracy of the thread elements are really, really important. So this is most commonly referred to as the machine fit. So to visualize this in just a little bit different fashion here, you'll see this visual representation, which, as you can tell, the numbers for each class, of course, continually progress themselves down, meaning that the allowance is a little bit smaller. Also, you can see that there are letters included in this call, which is going to be the next topic of conversation here. But finally, you'll see, of course, the allowance for fit, which is given for the externally threaded products. So the next up is the thread type. These are just two simple letters. It's either A or B. A is the call out for external threads, such as that on a bolt, and B is the call out for internal threads, such as that on a nut. And then finally, we've got the availability for a modification designation. So this is rarely used, but it's still really important when it's actually needed. So this modification allows for the adjustment of a call out of a specific thread when the standard nomenclature doesn't allow for it. So the most common thing that we'll see in our world is LH, when basically we're trying to call out for a left-handed thread. So before I move into the metric nomenclature system, I want to just pause real quickly to see if there are any questions or any comments that people would like to bring up. So I do see a question that popped in here by Rick. The first question is the pitch diameter exactly centered between the major and minor diameter? And the answer to that is yes. So basically, there's a theoretical line drawn in between those 2 points, the major and minor diameter, and then the distance between those laid horizontally across the thread component is measured. So next question is, will we be covering non-standard threads and pipe threads? Within the scope of this conversation, we're not going to. I am going to be running a subsequent webinar where we will address that. Of course, non-standard threads and pipe threads and tapered threads and all of that are also a very important part of this world. But today we're going to keep things real basic here. So the next question then that just came in here, and thank you, Pete, for that, is the nominal diameter the same as the major diameter? And the answer to that is not necessarily, right? Because the nominal diameter is, of course, what the call out, the specification is supposed to be. The major diameter in practicality, of course, is going to be subtly different than that. But for practical and theoretical purposes, Pete, yes, that's basically what's being specified there. And then the next question is, can the modification symbol be used for any dimensional modification, or are there limits to this symbol's use? That was sent in by Daniel. So excuse me while I consult my my technical crew here. So according to the response I just got, it's not something that we've ever really seen, but that doesn't mean that it's necessarily not possible. But basically, simply put, as we see thousands and thousands and thousands of thread plugs and thread gauges in through here throughout the years, and we've not seen it, it's probably not a very common practice that's being applied. All right. Well, hey, I really appreciate the number of questions that just popped in right there. That's awesome. That's certainly going to help us out, as we go through this presentation. So please, like I said, do not hesitate to ask if you've got any questions that are coming in. All right. Next up, we're going to dive into the metric designation nomenclature system. So again, this is pretty much what everyone else in the world outside of the US utilizes to specify thread components. So for those of you that have customers that exist outside of the US, or are beholden to a standard that exists outside of the US, this is certainly going to be a very common thing. Of the things that we see here at Fox Valley Metrology, this probably makes up approximately 20% of it. So it's not that it's entirely common, but it is certainly prevalent throughout the rest of the world. It's definitely worth discussing here. This is a very similar nomenclature setup as exists within the imperial side of things, but there are some key differences. So why don't we go ahead and break those down? So the first item listed within this designation is the thread series, as you'll see here, denoted by M. There are basically a handful of different types of thread series which exist, and this is pretty similar to what was like the UN and the UNC within the imperial system. So the first one and most common one is the basic thread profile, as is specified in ISO 68. If you guys are interested in learning more about that, obviously you can simply head to our website to look up ISO 68, or as well anywhere on the internet and see some of the specifications that are called out there. The next is the MJ profile, which is the MJ profile is a round root on external threads and thread ring gauges. And then the MJS is very similar to that as well. So the next nomenclature call out on here then is the nominal diameter. This is pretty much the same as what was given in the imperial system, that it is a theoretical diameter. However, the only subtle difference here is that it is listed in millimeters. And then next up, we have the thread pitch. So this is, of course, the first major variance between the metric system and the imperial system. If you recall, in the imperial system, we called things out as thread per inch. In the metric system, we're calling it out as the thread pitch. And again, the thread pitch is the distance between the same point on two adjacent threads of the thread form. This value is also listed in millimeters. Then the next item on the designation is the class of fit. So we're going to see a little bit of variance here in the next few things between the metric system and the imperial system. So the class of fit, again, like the imperial system, exists on this spectrum between a loose fit and a tight fit. However, instead of 3 designations, there are 5 designations given commonly. So the first item listed here is number 8. So this is for very loose applications, available for both, and it's available for both internal and external threads. 7 is for mostly loose applications. 6 is the general use classification. This is by far the most common class of fit. And again, it's really used for just general use. It's available for both internal and external threads. Class 5 is for pretty accurate applications. This is, however, is really only available for external thread callouts only. And 4 is, of course, the most accurate applications, and it's available for both internal and external threads alike. So a good visual representation of this right here is shown. So as you can see, as the number gets smaller, so does the acceptable allowance given to that class of fit. Next up then, we have the allowance adjustment. So this is probably the biggest deviation that exists between the metric system and the imperial system. So basically, when we're talking the allowance adjustment, you're going to think about this like a bucket for each class of fit. So this allows us to further modify and really hone in on exactly what we're trying to get at with the acceptable allowances within a given thread. So whereas in the imperial system, there's really only one call-out designation for that. So there are 4 primary categories for this. We have the letter E, which is for very loose applications for external threads. The letter F, which is for very loose applications for external threads, or I'm sorry, not very loose, just regularly loose. G is for common use internal threads and loose application of external threads. And H is for common use on external threads and for accurate application of internal threads. So most commonly, we're going to see G and H as the callouts on thread designations within the metric world. But of course, we have the availability to utilize and call on any of the other allowance adjustments that are listed here on this page. However, there is one further piece of information that is hidden within this allowance adjustment, and that's the case of the letter. So if that letter is actually shown as a lowercase item, that is going to be a call out for an external thread. And if that item is uppercase, that's going to be a call out for an internal thread. So since this concept is obviously quite a big deviation from the imperial system, and one that might be new to a couple of you guys on this call, let's show this out in a visual representation listed here on this page. So as you can see, here are each of the different classes of the allowance, along with their class of fit listed along right within it. So on external threads, you can see that that's a lowercase callout. On internal threads, that's an uppercase callout. And as mentioned, on external threads, we have a designation to allow the class of fit to be called out along with each one of those allowance adjustment buckets. Whereas on internal threads, it's classes 8, 6, and 4. So as you can see here, we're going to come back to this and you'll see that it's called out as the class of fit is 6. The allowance adjustment is H. And you can see, of course, that it is an uppercase instrument or uppercase call out in this designation, which of course designates that this is going to be an internal threaded component. Finally, we've got a call out for the modification of this. Again, this is very similar as to the imperial setup. It's rarely used, but it is there when it is needed. So before we change gears and go into the thread inspection theory, if you guys have any questions or if anything's popped up so far, let's go ahead and address those. So I see the first question that popped in here is, will we be discussing set plugs or work plugs? So we're going to be discussing primarily work plugs, but setting plugs are going to come up in conversation later as we discuss the adjustment of thread rings. And if that went over your head for right now, we'll of course address that in more detail here in just a minute. So the next question on here then is, I see true position maximum material condition on threads all the time. How would we go about measuring that? So I'm going to kick that over.
I'm going to actually have you send Laura.
Okay. So Brad, that is an excellent question. One that's got us a little stumped right now. I think I'd take a good chance at answering that question, but I don't want to go ahead and give you any wrong impressions here on this call. So what I'm going to do is I'll send that over to our lab managers. They'll make sure that they get you a good technical response on that. So Josh, if you want to go ahead and make a note of that, we'll make sure that that gets addressed directly to Brad. So appreciate that question there. All right. So with that, we'll dive into thread inspection theory. So as you guys have seen, threads have a rather complex geometry for something that is just so basic to our existence, right? I mean, everything you guys have ever worked on has involved a threaded component, right? Whether that be nuts and bolts, whether that be screws, whatever it is, this is such a common thing. But really, until you dive into it, and myself personally, really until I dove into it, did I not fully understand how complex this world can actually be. Well, of course, as all of you guys know, with complexity comes frequent error, right? So as you're manufacturing threaded components, there are multiple common sources of error. The first is eccentricity. So basically what this is when the pitch diameter of a thread is not directly concentric with the axis of the thread. You can see here, of course, on this representation, how much that would actually impact the outcome of the final product. The next would be the flank angle. So most commonly, the flank angle is designed to be 60 degrees. And as you can imagine, any variance from that specification affects the actual functional size of the finished product, as represented by the dotted lines, the dashed lines, I apologize, as you can see on this image here. So the next common error is roundness. So this comes in many different forms, whether that be ovality or even the erratic form that is shown here. So regardless of the type of roundness error that shows up in it, in order for the thread to be perfectly functional, it must exist within the maximum and minimal dimensions that are shown by the dotted lines here within this presentation. So any variance outside of that is, of course, going to cause that component to fail its intended design. And finally, we've got pitch diameter. So this is actually the most common type of error that exists within the manufacturing of a threaded component. Also, it happens to be the most critical dimension when it comes to mating two threaded components together. So this is one that we definitely need to focus on and worry about as we're inspecting threaded component manufacture. So basically what happens is all of these common sources of error essentially just stack on top of themselves. And this becomes a very accumulative error, which ultimately affects the functional size of the threaded component. And this functional size is what really needs to be focused on and discussed here, because this is the most important criteria as we're discussing the actual application of a threaded component. So basically, the functional size is what's actually going to determine whether or not it fits with its mated component once the final assembly is put together. And like I said, the functional size is really determined by how accurate are all of these different errors eliminated out of the design and out of the manufacturing of the actual component itself. So if you were wanting to go out and try to get an actual reading on all of these threads themselves, you would use what's either called the ball method or the wire method. So basically, as I mentioned before, the most important dimension that we're going to check within a thread form itself is its pitch diameter. Again, this is what's going to have the most bearing on the actual fit along with the mated component of the threaded component that you're checking. So basically what this is done is by placing a wire onto external threads or a ball onto internal threads. So the wire or ball is placed between adjacent flanks of a thread at a point that rests on the flanks at the pitch diameter. So essentially, in the case of measuring external threads, you'd measure the distance from wire to wire, and then you'd subtract out the constant of that wire. However, this measurement method has two major flaws. First and foremost, it doesn't take in all of the above irregularities that we just mentioned on measurement error into consideration. So therefore, it's not actually a functional check. Also, as you can imagine, this is really time consuming. I mean, in order to go ahead and inspect this, you'd have to take these parts off of the shop floor into your inspection room. You'd then have to set up the equipment for it. Of course, you'd have to have all the appropriate equipment in the first place and go ahead and just inspect one individual component at a time. That's just not a practical use or a very good way or good use of your time within a given day to go ahead and measure the many, many threaded components that you guys are probably rolling out on a daily basis. So the good news is there's actually a much, much better way of going about this, and that is, of course, thread gauging. So there are two common types of thread gauges. There's thread plugs and thread rings. But both of these really are all considered attribute gauges. So this means that we're not providing the exact feedback on what those individual measurements are. However, what we're doing is checking it in a go and no-go fashion. So simply put, the go member of the thread gauge should either go into or onto the threaded component that's being inspected. And the no-go member should not do that same thing. So then by utilizing this very quick, very efficient inspection method, that if the go end is able to go into or go onto the part and the no-go end is not able to, that component is good. You might not know the exact size, but essentially what we're getting at here is it really doesn't matter, because you're going to know that it fits within the acceptable tolerance of that component very quickly, very, very efficiently. Also, most importantly, this is going to be able to be done right out there at the shop floor, which means that your actual machinists are going to be able to do these inspections and these checks right there really quickly without you even really having to get involved. So that's what makes thread gauging some of the most common pieces of equipment in the manufacturing world. And certainly some of the most common things that we see here throughout Fox Valley Metrology. So as I mentioned, there are thread plugs, and of course those are used to inspect internal threads. And there are thread rings, which are of course used to inspect external threads. So before I move into a deep dive of both thread plugs and thread rings, I'd like to pause again really quickly. If you guys have any questions, please feel free to go ahead and throw those in the Q&A. I do not see that there are any questions sitting there waiting right now, but if you guys do have any questions, please feel free to throw that in there right now. Okay, looks like we're good. So with that, we're going to dive into a deep discussion revolving around thread plugs and thread rings, basically how they're designed and how you would go about using them. This is really good information for all of you guys to have, so that way you can pass it forward to anyone who might be new to your company or new to machining in general, or to pass on to some of the more tenured people to make sure that they're actually utilizing these items correctly. Again, these two things make up a very large majority of the things that we see here at Fox Valley Metrology on a daily basis. And it really is some of the bread and butter of the machining world. So having a really good understanding on how these are all utilized is incredibly important for everyone that's going to be involved in manufacturing. So when we look at thread plugs, first and foremost, basically everything you're looking at here is commonly referred to as the assembly. So the assembly is made up of a couple different components. First, you've got the go member, then you've got the no-go member, and then of course you've got the handle. So let's talk about the members themselves and how they're actually designed. The first and most common design is the taper lock design. So basically this allows for really quick, easy replacement of a worn member, which does happen often. And we're going to talk about in a little bit what happens when a member gets worn down. The next most common design is the reversible design. So this actually contains threading over the entire length of the member, as opposed to the taper lock design, which only has threading over the end of it. So the benefit of the reversible design is it can actually be reversed within the handle itself once one side of it has reached the end of its usable life. So basically, as that item wears down and it fails calibration, you could actually turn that around and be able to utilize that in a similar fashion, essentially doubling the life of that member. So this is a really good idea for very high volume applications. And next, we have the tri-lock design. So basically what this is there's a bolt that threads in along the axis of the member, and it locks it into the handle. So this system is really best suited for very large thread plugs, typically over an inch and a half, because simply put, there's not going to be a handle that's designed in a reversible or a taper lock design that can address rings that big, plugs that big. And we very commonly see items over an inch and a half. There are some very, very large manufactured threaded components out there that are of course going to require a thread plug that is correspondingly as large. So due to the size of these plugs, it's not uncommon at all to see them as individual plugs, as what's shown here, rather than having a go and a no-go on either end of it. Obviously, as those things get very large, they get heavy. If you were to put both members on the same plug itself, obviously that item would become heavy past a point of feasibility to use. So as for the Go member itself and how it's designed, it's actually machined to a plus tolerance, which makes it so that the member exists inside the maximum material limit of the internally threaded component that it's inspecting. So this member is actually commonly designed longer than the no-go member due to the fact that it's intended to thread through the full depth of the threaded component. Also, it's oftentimes machined with a little groove in it. So that groove is there to is present, I should say, to allow for the easy clearing of any debris that might exist within that threaded component. And all that really does is prevent any unnecessary wear on the gauge and, of course, on the component itself. You can imagine that if that didn't exist, any leftover debris from manufacturing or anything like that is going to sit in there and it's going to grind on both the gauge and the component itself, obviously wearing things down much faster than they would ever really need to. So the Go member is specifically checking these attributes of the thread form: the minimal allowable major diameter, the minimal allowable pitch diameter, the flanks, and the lead of the internally threaded component itself. So how do you actually use a Go member in your thread plug? Basically, what you're going to do is you're going to simply take the thread plug and thread it into that internally threaded component. It should thread through the part, or thread into the part rather easily. And really, it should pass all the way through. It should be done without the use of force. If not, the part fails. Now, it's incredibly important to talk about this in a little bit more detail here, especially referencing the without the use of force line item there. Simply put, it's not going to do anyone any favors if you're going in there with that thread plug and you're really wrenching that thing in there, maybe even have to grab a wrench to actually help tighten it through, and hey, look, the part passed. Well, frankly, that's probably making you accept a part that should have failed. Also, it's going to just simply wear down your gauging much, much faster as a result. So it's really important that you guys understand, what the without the use of force really actually means. And simply put, that's kind of based off of feel. That there should be a level of understanding what that should be across your company. And of course, that might involve you or the quality manager or whomever is kind of dictating this to really help define that to all of your staff and all of the machinists to make sure that they understand this detail in much more detail. Because again, if they're going through and they're really wrenching this thing in there just to make it go, and you guys are passing product that should be failing, there's of course a pretty severe liability that exists out there at the end of the day. So as for the no-go member, this of course is kind of the opposite, the yin to the yang of the Go plug member itself. So this is machined to a minus tolerance, making it so that the member is at the minimum material limit of that internally threaded component. It's commonly manufactured shorter than the Go member, as I mentioned just a bit ago, because it's not actually needed to go all the way in. And simply put, shorter equals cheaper. So why make something longer or bigger than it needs to be? And then you guys can ultimately save some money on that gauging there. So often this is actually machined with a ground down crest, as this portion of it isn't actually needed to be used within the inspection. So you can see here that it doesn't come all the way to the end of that threaded component. The no-go member is really only used to check one attribute on the internally threaded component, and that's the maximum allowable pitch diameter. So how do you actually use the no-go thread plug? So as I mentioned multiple times already, this should not thread into the actual threaded component. So what does that actually mean? Well, it's actually separated into two different classifications on that, one for imperial and one for the metric designation system. So in the imperial world, this means that you shouldn't be able to thread that no-go plug in more than 3 turns. And the metric system defines this by saying that it should have a definitive drag before the second turn gets there. Now, again, you guys need to be able to use a good sense of what this should be. Now, if it's stopping, but it's only stopping because you're really putting any effort into it, you probably shouldn't be passing that part. So again, this should really be defined out at the quality department level and making sure that everyone in the company that is utilizing thread gauging fully understands what that looks like. Because again, if it doesn't go through, or if it turns on to the part, or into the part, I apologize, more than 3 turns, or it doesn't have that definitive drag before the second turn, that part really should be failing inspection there. So before I move into thread rings, are there any questions that we want to address within the thread plugs side of the world? Go ahead and use the question and answer option on the left side of the screen. I do see a question had rolled in by Aaron asking whether or not this PowerPoint is available for download. I am going to be sending this out in video fashion. I've not set up anything right now where the PowerPoint itself will be available, but that's certainly something that I can look into and be able to send a link out to that. So great question, and absolutely I'll be able to make sure that this is available for you guys. So next question that popped in. If the thread is too tight to fit with the Go member, it's an important reminder to chase the thread with the tap once again, as there could be a chip caught in the hole. Yep, and that's an absolutely great point. So Tom, I really do appreciate you bringing that up. So basically what he's getting at here is if the Go member is too tight to fit in there, it is possible that there could be just a chip caught in that. So run the tap through once more, and that might actually clear things up and be all that you need to get the part accepted. So appreciate that input there, Tom. So with that, why don't we dive into our discussion on thread rings? So thread rings are often sold as sets. Instead of how they were done on the thread plug side of things, obviously there's not really a good way we could put a handle onto 2 thread rings. So they're often sold as set. One is a go and one is the no-go. So as far as the design of the thread rings themselves, there are a couple different common designs. The first is fixed. So these rings are designed to be fixed at their exact size. Good news is these are often cheaper than their counterparts. The bad news is you can't adjust them, right? They are what they are. However, there are also adjustable rings, which came about, I believe, shortly after World War II, which addresses some of the problems that we just mentioned within the fixed side of things, that these actually can be adjusted. This, of course, is in contrast to the thread plug. But the good news of this is, let's say that the gauge itself is just slightly not perfect and fails calibration right away. You can actually adjust that ring right off the bat and go ahead and make it a usable gauge for you. Additionally, as the gauge wears down over time, you're able to adjust that and bring that back into tolerance. We're going to discuss that quite a bit here in just a minute. So let's just talk about this adjustable thread ring design itself. You'll see there are a couple different key components to this. First and foremost, you've got the locking screw, which basically has to get undone every time you're about to adjust it. Next up, you've got the adjusting screw itself, which is what's going to control you and allow you to make adjustments on the thread ring. Next up, you've got the locking slot. And then finally, you've got the spring holes. So this is what allows for actual leeway within that adjustment. So you'll see here that this picture does have some wax in that locking screw slot. It's really a best practice to place some wax in those screw slots. First and foremost, it does a couple different things for you. Primarily, it's going to go ahead and protect those screws from getting damaged. Obviously, these things are getting used out on the machine shop floor. So you want to make sure you protect that part as much as you possibly can. Additionally, it provides you tamper-proof evidence, right? So if you have that wax on there and it's still in there the next time you need it, you know that that thing hasn't been adjusted and brought way within or way without of tolerance just by accident because somebody didn't know what they were doing. And additionally, it's really nice if you go ahead and you use go for the green gauge, green for the go gauge and red for the no-go gauge. It allows for very quick, very obvious identification of that particular gauge as somebody's about to grab it to make sure that they're not accidentally using the wrong item. Now back to some of the common designs. The next most common one we see, although not nearly as common as fixed and adjustable, is just the Southern design, specific to some manufacturers that are out there. We won't go into a whole lot of detail about that particular item. All right, so let's talk about the design of the Go ring itself. This is actually machined to a minus tolerance, so it doesn't exceed the maximum material limit of the externally threaded component that it is inspecting. So it's designed to inspect the following attributes: the maximum allowable minor diameter, the maximum allowable pitch diameter, the flanks, and the lead. So how do we actually use the Go ring? Well, you can imagine this is going to be very similar to the Go member of thread plugs, just for externally threaded components as compared to internally threaded components like we discussed on the thread plug side of things. So this, of course, should thread all the way onto the part. And as mentioned before, it should go all the way across the entire length of the component without the use of any substantial force. If not, the part fails. Same conversation applies here as it did on the thread plug side of things. If you're using a ton of force to make that item go on, it's not doing anyone favors. All it's doing is wearing down your gauging, and also it's causing you to pass items that probably should not be. So as far as the no-go ring is concerned, let's discuss the design of that. This is actually machined to a plus tolerance, making it so the member is at the minimal material limit for the externally threaded component. Commonly, this is machined with a ground down crest, as this portion of the thread plug, or this portion of the ring, is not needed. So this is very similar as it was on the thread plug side of things. As you can see, the ring material does not go all the way into the groove of the externally threaded component. Again, less material, less cost. And again, the no-go ring, just as its counterpart within the no-go plug side of things, is only used to inspect one attribute, and that's the maximum allowable pitch diameter of this externally threaded component. So actually utilizing the no-go ring is, of course, again, very similar to that of the no-go thread plug. It should not thread onto the part that you are trying to inspect. So for the imperial system, again, that is less than 3 turns. And for the metric system, that's defined by needing a definitive drag before the second turn. If either of those don't come through, the part, of course, fails. So as I've mentioned a couple times, we actually have a benefit available to us that thread rings can be adjusted, of course, if they are designed as the adjustable thread rings. So what really happens with that is essentially over time, as the thread gauge is used, you're rubbing metal against metal. And over time, what's going to happen is that thread ring is actually going to wear down. And as you can see here, that eventually just kind of forms a little step within the ring gauge. Now, this might be imperceptible to the eye. I know it makes obvious sense here looking at a PowerPoint, but in reality, it's going to be very difficult to see this. That's why, of course, regular calibration of your thread rings, and of course, even your thread plugs too, is strongly recommended. But fortunately, for adjustable rings, we can, of course, worry about this step that's being built into the ring gauge itself and adjust it so that way the ring gauge is brought back into tolerance. Of course, for plugs, that's not an option for us. So once plugs are worn out, they simply just need to be replaced with a new member for the size that you're looking at. So how we actually go about adjusting thread rings is by utilizing a thread setting plug. So it's important to discuss the distinction between the set plug and the work plug. I believe that was something that was brought up earlier in a question here. So the thread set plug is actually designed at the nominal tolerance or the nominal size of the thread itself. It is not designed with the plus or the minus tolerance as the go and the no-go members would be of a working plug. So I hope you guys understand that important distinction there. This is a set plug that is being used to actually adjust thread rings back together, back to within tolerance, I should say. And again, you do not want to use this as a working plug, as it's not going to give you the actual intended result of what a working plug is designed for. One thing that we do recommend here at Fox Valley Metrology is that if you are purchasing a thread ring, it's important that you also go ahead and purchase the corresponding set plug for those thread rings. Now, of course, if you have the same quarter-20 thread ring all across your shop, you're not going to need an individual set plug for every single one of those items. One will probably suffice for your whole company. However, as you get into more uncommon sizes, it's really important that a set plug exists because, as we talked about before, without it, it's incredibly hard to calibrate and tell the actual size of that thread ring. While it can be done both on your end and on ours, it's not going to be a functional check. So you need to make sure that you have this set plug available for it in order to regularly inspect your thread rings. So that way, the ring that you're utilizing to inspect your finished product is actually within tolerance and you're not passing and failing items that should not be passed or failed. All right, so the most common design for a thread set plug is the truncated design. So you'll see here that the truncated section of the thread set plug actually has the crest ground flat. So here's what this would look like as it's being mated into its corresponding thread ring. You can see the truncated section does not go all the way to the bottom of the thread form, whereas the full form section, of course, does. And this is designed so that way the truncated section contacts the flanks of the rings within the wear plane, almost as if there was a product being threaded onto the ring. So as we talked about, that wear plane basically creates a little step in this. We want to make sure that we're checking both that beginning portion of it as well as the full form where the threaded component has not worn down that ring, past that step. So that's where the full form comes into play, which of course is going to check the contact of the flank across the entire portion of the gauge. So basically the process of how you would go about adjusting an adjustable thread ring is not super complicated. There's a lot of really good resources available to you out there. Today we're not going to be showing a full demonstration of this, but I can walk through really quickly on how this actually works. So it essentially boils down to this. First and foremost, you're going to open the locking screw. Secondly, you're going to adjust the adjustment screw clockwise to turn the ring open to a larger diameter than what the actual plug itself is coming into. You're then going to turn the ring onto the setting plug until it is gauged with at least one thread of it extending beyond the last thread of the full form section of the thread set plug. And then you're going to turn the adjusting screw counterclockwise until there's a slight drag between the ring and the setting plug. You're going to then retighten the locking screw and go ahead and test it out. Now, obviously, this might be a little bit of an iterative process if you don't get it perfect the first time around. But really simple, pretty straightforward process available there. So before I move on, are there any questions regarding thread plugs or thread rings? If you do, please go ahead and use the Q&A section on the left side of your screen. So the question that popped up by Jeff here is there a rule of thumb for the amount of force or torque for a Go member? And the reality is there's not a definable metric for that, but basically what we use internally is just essentially a two-finger drag, meaning if you can see me on the screen here, that you want to just use your thumb and your forefinger or your pointer finger and basically just turn that on. If it takes any more force than that, you're not going to want to go ahead and pass that item. That's pretty much the best that can be done for this inspection here. And again, that's really the purpose of this all, is that we're not trying to be incredibly precise with this. We're just trying to have something that's pretty quick, pretty down and dirty. But again, to summarize, if you can use your first two fingers, your thumb and your pointer finger here, and be able to turn that, everything's going to work fine on that. All right, I don't see any other questions popping in, so we will go ahead and jump back over to the presentation. So now that you know pretty much everything you need to know about inspecting threads on the shop floor utilizing thread gauging, where would you actually go about in getting them? Well, there's a lot of different manufacturers that exist in this world, but some of the more common ones in the industry that we see: Vermont Gage, Thread Check, Westport, Glastonbury, Southern. All of these guys are excellent manufacturers out there. And the good news is Fox Valley Metrology actually supports all of these brands as well. Even if something's not listed on here, I guarantee that we've got a direct relationship with them set up. And even if we don't, something that will very easily be able to get set up as needed. So typically speaking, when a request comes in, we're going to go out for quote and help you guys find not just what the cheapest item is out there, but what's going to be the highest quality, and of course, what's going to have the best turnaround time at the current moment being requested. So the good news is since you guys have all sat on this call and taken a good hour out of your day to listen to me basically just ramble on here, we're going to be offering everyone on this call a special promotion, one that we're really excited about. So if you are interested in purchasing some thread gauging for your needs, we're going to be offering free calibration on your next thread gauge order. That's available to be redeemed by visiting www.foxvalleymetrology.com/thread. This offer is going to be available to each and every one of you through the end of October. So really 2 full months here to go ahead and capitalize on this. So obviously, this is going to knock off, sizable amounts of cost off of any order that you have, depending upon how large the order actually is. So very exciting offer, one that I definitely recommend each and every one of you guys taking advantage of. And again, it's really just a thank you for making this call as great as it was. And I do truly mean that. Guys, there was over 75 people on this call here this morning, which is just fantastic. When we started this webinar series several months ago, our anticipation was getting hopefully 20 to 25 people on each and every call. So having 75 individual people logged in, not to mention how many people might be joining them within the room, it's just absolutely tremendous. And we do really, really appreciate your guys' participation in this and the conversations that have come about from it. So just a couple things I want to touch on as we wrap up here. We do have training available. If you guys want to go more in depth into the items that we discussed here today and learn more about that, maybe even setting up something specific for all of the people in your quality department or even all of the machinists in your company, by all means, we're available for that. All you would have to do is reach out to myself, anyone else at Fox Valley Metrology, go to our Contact Us page, and just let us know that you're looking forward to that. And basically what we would do is we would tailor a presentation specifically to your guys' need. We'd be able to host that here at Fox Valley Metrology, or we'd be able to host it right there at your facility as well. So like I said, please just reach out and we can absolutely work towards coming up with an agenda for what something like that would look like. As I mentioned earlier, our next webinar is coming up next month on September 29th at 10 a.m. And the title for this is SPC in 3 Steps, Learning Statistical Process Control. So that's going to be hosted by Midatoyo, where we're going to be going into a deep dive of SPC, what it is, why it's beneficial, and basically, how do you go about doing it? What are the best methods to collect the data? What are some best practices? What are some of the systems that exist out there? And finally, as I mentioned just a second ago, please feel free to take advantage of the special promotion that exists out there right now for free calibration on your next thread gauge order. Again, all you got to do is visit foxvalleymetrology.com/thread. There's going to be a simple form on there for you to fill out, just asking for your name, your email address, and basically what type of thread items you're going to be looking for. There's going to be a redirect right at the end of this webinar that sends you directly to that page. So if you are interested, just hold on and it's going to automatically send you there. Also, there is going to be an email that goes out that has a link directly to that. And of course, you can always just reach out to anyone here at Fox Valley, whether that be myself, whether that be your local sales rep, whether that be anyone in a logisticals position that you're used to dealing with, or even just come into our Contact Us page and ask more about that. And you'll be able to take part in this special promotion that we've got running. And again, that's going through the end of October. So your next order, as long as it's placed by the end of October, will be eligible for this promotion. So with that, I just really want to thank you all again for the time that you took here today. I really hope that this session was as informative as it was for you, as it was for me, just going through and really pulling all of this together. Even having been around this world and this company for my whole life, there were things that I learned just going through this process. So it was really exciting, and I hope it was for you guys as well too.